20 years ago we couldn't imagine the existence of the smartphone, and now we can't live without one. The number of Internet of Things devices in 2021 will reach the eye-opening 46 billion. Consequently creating more and more e-waste, around 50 million tons of e-waste generated each year. And what impact will this have on our planet? Firstly, e-waste can cause harm to humans and environment, such as heavy metals contained lead, cadmium and chromium. Secondly, while the Earth's resources are finite, the value in e-waste is untapped. If those trends continue, by 2050, we'll have to deal with 110 million metric tons of e-waste every year. Up to a fifth of all e-waste moves around borders, likely ending up in countries where workers process it at illegal dump sites, such as Ghana, India, Pakistan, China. In those places 40 million tons of e-waste are discarded in landfill or illegally traded every year. By investigating the informal recycling process, we found that workers were extracting metals by burning and dismantling e-waste, which led to burns, back problems, and wound infections. 20% of the world's e-waste is still formally recycled, which is a safer, more efficient, and need more financial resources process. When comparing the two different methods of recycling, we find that informal recycling still predominates, although formal recycling is far more efficient and environmentally friendly than informal recycling. However, the illegal trade in UK shipments to Ghana shows that e-waste is often dumped in less developed countries in order to reduce investment in recycling waste in developed countries. An analysis of the UK's annual e-waste exports shows that mobile phones are the most frequently updated and used, and make up a relatively large proportion of e-waste. In addition, mobile phones contain a large number of precious metals, which have a higher recycling value and would cause serious environmental pollution. Although mobile phones are a huge hazard when turned into electronic waste, the global market is still producing, consuming, and updating mobile phones more frequently. The UK is a consumer country with an advanced economy and very high purchasing power. London, the most consumer-friendly city in the UK, has a strong consumer culture but a lack of recycling culture. Of these, the manufacture and consumption of mobile phones in London is particularly strong, with around 6.8 million phones being discarded during the year. The high street, the epitome of the British bricks and mortar economy, has been in decline for the last 10 years as people have moved from physical to online consumption with the increase in the Internet of Things. Therefore, the lack of recycling culture and the decline of the high street are our main concerns. The closing shops on the high street have proved that revitalizing the high street with traditional consumer spaces doesn't work. So could we reprogram key high street areas from place of consumption to place of recycling and production? What will we do? Recycle and reuse are currently missing from the circular economy and does not form a closed loop. The value of e-waste is returned to the recycler through formal recycling and the metal resources are put back into production, creating a circular economy. The value of e-waste is returned to the recycler through formal recycling and the metal resources are put back into production, creating a circular economy. Our design will therefore be integrated with the closing down of shops on the high street, encouraging people to recycle offline, driving the real economy, promoting recycling culture and bringing prosperity back to the declining high street. We used K-means to develop relevant characteristics to find sites from the 64 sites that had high footfall, convenient transportation, dense cultural sites and were on a declining high street. It was eventually located in Cluster 6 and further site analysis was carried out on this cluster. Based on a combination of factors such as the range of mobile social media distribution and usage, people type in the site, income levels, and literacy levels to select the high street for our interventions. Finally, the design was located in the Kensington area of London. At the same time, the UK government has developed policies to support decaying high streets. Of the high street locations supported by the government, we found through our research that Harrow Road has the highest rate of shop closures. We then extracted the building outlines of all the closed shops on this high street. Analysis of the light, connectivity and the number of inhabitants within a 500 m radius of the building. A small range of buildings were then scored together and the highest scores were given to our conversion sites. We use machine learning to transform the consumer space of the high street into a space for recycling and exchange by combining the recycling and consumer space planes. First, we divide the consumption space and the recycling space into four separate space types. Second, by using pix-to-pix, the two spatial types are merged to obtain a new model. We divided the space types of the different commercial and recycling spaces according to the above rules as pix-to-pix input dataset. Finally, the building outline of our design site is used as input and the machine calculates the functional zoning of the site after integrating the consumption and recycling functions. Today's formal recycling process is led by robots, so to combine this process with the high street, it is important to pay attention to the space in which used by the robots. Therefore, we transformed the human-scale consumption and recycling space into a grid framework suitable for robotic movement. In the output of pix-to-pix, processing space, transportation, and storage space are designed for robots. Finally, the iterative process of pix-to-pix is accumulated and the net architecture for robot movement and handling is formed. The basic cell of the network architecture for robot movement is a 0.42 m square frame. In the machine system, the cells can be switched between as few and as many as required, and metal blocks are constantly installed and removed within them. The spatial form is subject to the constant change in the temporal dimension. The smaller machine movable frame units are able to adapt to a wide range of complex architectural contours. Within the limits of the existing building outline, the robot space is deleted and the remaining part is metal storage space. The metal storage space is used to store valuable metal elements extracted from disused mobile phones through the formal recycling process, namely silicon, iron, aluminium, copper, and nickel. The metal will be stored in the building as a unit according to the robotic grid unit and will be placed in the building according to the different storage requirements. The combination of the mesh framework generated by pix-to-pix and the blocks for storing the metals will result in a complete building form. The building will grow on top of the original high street building and its interior contains the formal recycling process for mobile phones. Firstly, the shape of the original building will be preserved and passers-by will be attracted by the robots in the windows. The interior of the original building will be used mainly for recycling culture promotion and mobile phone collection, so that mobile phones can flow through the building. Old mobile phones enter the building and are transported and processed by the robots without human involvement. Located in the center of the building is the General Control Office, which manages and operates all the robots in the building. The old mobile phones that are recycled into the building will be processed by the robots into valuable metal. These metal parts will be treated as building materials and grown in the building through robotic 3D printing. Our buildings will continue to grow vertically as the number of recycled used mobile phones increases. The metal blocks can be dismantled from the building as required and returned to the recycler as physical value or re-involved in manufacturing as raw material. In the end, our design will become an urban mine, interspersed with different types of metal. Through the new metabolism of the building itself, the waste will be extracted to its physical value, bringing sustainable benefits to the city as a whole, and finally, the cause of the high street's prosperity will be transformed from consumption to recycling. A global problem solved through localization. Ultimately, the urban mine will improve recycling rates and economic conditions across the high street, and not only that, but will have an impact on the global e-waste problem, localizing the global problem.